Hello, friends. Before we begin, I want to ask you something. Look at the device you are using right now. Do you think this computer can solve every problem in the world? The answer is no. And that's exactly why quantum computing exists. Now, imagine this. You're searching for a key in a house with 1 million rooms. A classical computer checks one room, then the next one, and then go to the next one, which is very fast but still only one by one. So here, searching for a key in all the rooms will be done one after the other. What if a computer could check many rooms together? This is where quantum computing begins. Quantum computers don't think in single path. They think in possibilities. They are built using the rules of the quantum world, where particles behave in strange but powerful ways. Quantum computing is a new and powerful way of computing that is based on the laws of quantum physics, the science that explains how particles behave at very small scales, like atoms and electrons. In a normal computer, information is stored using bits. Each bit can be either 0 or 1. But in quantum computing, we use qubits or quantum bits. A qubit is a special one because it can be 0, 1, or both at the same time. This unique property is called superposition. If you observe this picture, it shows how quantum physics, advanced chips, and digital systems come together to create a powerful new kind of computer. The atom at the top, it represents quantum mechanics, subatomic particles like electrons or qubits. The orbits symbolize superposition, which means many states at once, and entanglement, where particles connected across space. This shows that quantum computers work using the laws of physics, but not just electronics. And the vertical beam of light, it connects the atom to the chip below, and it shows flow of quantum information, transformation of quantum states into computation. It visually explains how quantum behavior powers computation. And the quantum chip at the center, it's a glowing chip which represents a quantum processor. Unlike normal chips, it processes qubits, not just bits. It handles many possibilities simultaneously, and the bright core symbolizes immense processing power, high energy quantum operations. So, this is the brain of quantum computer. And you can even see this circuit line spreading out. So, it shows data spreading in all the directions, massive parallel computation. Unlike classical computers, quantum computers explore many solutions at once. This highlights speed as well as scalability. And you can even find out the futuristic city below, which represents modern society, industries like healthcare, finance, AI, security. It shows that quantum computing will influence daily life, power future smart cities and technologies. And the dark space background is a vast universe symbolizes infinite potential, unexplored scientific frontiers. It suggests that quantum computing is still evolving. We are at the beginning of discovery. Before going into quantum computing, let us just have a look at how classical computers work. So, this type of problem solving is often referred to as input process output model, where we have three main stages. This is a starting point where data is entered into the system, and you can find out peripherals like keyboard, mouse, and monitor displaying binary code 01. The computer receives information from the user or another source. This information is converted into machine readable language, which is a binary code. And coming to the second one, processing. This is a brain of operation, and here you can see central processing unit. There is a microchip with internal components labeled as the arithmetic logical unit, which does the math, and the control unit, which directs traffic. The CPU takes the input and performs calculations or logical operations. Here you can see one time calculation or one calculation at a time. This means the classical computer solves problems sequentially. It finishes step A before moving to step B. And the last one is output part, which is a final result presented back to the user. A printer producing a document saying result equal to 42 and a smartphone screen displaying an on status. Here the process data is converted back into a human readable format, which can be in the form of text, images, etc. And again you can see classical machines solve problems fast, but only one problem will be solved at a time. Then, how quantum computing works. Unlike the classical computers, which process information linearly, which is nothing but step by step, quantum computers use the unique laws of quantum mechanics to process information in a completely different way. And there are five important stages here. First one is qubits. In classical computing, the basic unit is a bit, which is strictly a 0 or 1. In quantum computing, basic unit is a qubit. The sphere shows that a qubit can exist in a state that is complex combination of 0 1 represented by the arrow's position on the sphere. And the second one is superposition, a wave pattern with the text 0 and 1 both. This is the ability of a qubit to exist in multiple states at the same time, while a classical bit is like a coin resting on the head or tail. A qubit in superposition is like a spinning coin. It is effectively heads and tails simultaneously until it stops or until it is measured. This allows quantum computers to analyze many possibilities at once. And the third one is entanglement. Sorry, there is a spelling mistake here. It's entanglement. Here you can see two particles A and B. They are connected by arrows with the text spooky connection. Two qubits can become linked so that the state of one instantly affects the state of other, no matter how far apart they are. This allows quantum computers to process complex correlations between data points incredibly fast. Then we have quantum gates. Here you can observe a circuit diagram containing symbols like H, which represents Hadamard gate, and a plus sign, which is a C naught gate. Just as classical computers use logical gates like AND or NOT to manipulate bits, quantum computers use quantum gates to manipulate qubits. These gates rotate the probabilities, changing the state of the qubits to perform calculations while preserving superposition and entanglement. Then, measurement. An observation symbol is found here, which leads to a split between 0 box and 1 box, labeled collapse to 0 or 1. This is the final step. When you look at or measure a quantum system to get an answer, the delicate quantum state, which is nothing but superposition, collapses. The qubit is forced to choose a definitive state, becoming a standard classical 0 or 1, which is a final output result we can read. And these are some of the common quantum gates to manipulate qubits. First one is Hadamard, represented with symbol H. It puts a qubit into superposition or it creates superposition. If you start with a qubit at 0, the H gate spins it so it is effectively 0 and 1 at the same time with equal probability. This is important because it allows the computer to process multiple possibilities simultaneously. Then we have poly X, and the symbol used is X. It acts like a classical NOT gate. It flips the state. If a qubit is 0, it becomes 1. If it is 1, it becomes 0. Then we have poly Z, and the symbol used is Z. It applies a phase shift. It doesn't flip this value 0 or 1, but it changes the phase, which is a quantum mechanical wave of the qubit. This is important for quantum interference, which helps cancel out wrong answers and amplify right ones. And the next gate is C naught, which entangles two qubits. This is a multi qubit gate. It looks at a control qubit. If the control is 1, it flips the target qubit. If the control is 0, it does nothing. This creates a dependency between particles known as entanglement. And the last one is Toffoli. It's a controlled knot. It flips the target qubit only if both control qubits are 1. It is just similar to a classical AND gate and is essential for complex logic. And here you can see the workflow of the quantum circuit. There are total 4 steps here. First is prepare qubits, then apply gates, measure, and then result. Coming to the first one, prepare qubits. Here you can see qubit 0, qubit 3, qubit 1, 2, and so on. So they are actually initialized to the state 0. All 4 are initialized to state 0. This is like clearing the memory on a calculator before starting a problem. And second one is apply gates. This is the computation phase. The horizontal lines represents time for each qubit. And the boxes and symbols used here on these lines are the gates. So if you take this H box, it is used for creating superposition. And the plus signs, these are the C naught gates. They connect two different horizontal qubit lines, creating entanglement between them. And then we have X connected lines. In the middle of the diagram, you can find out X marks connected by a vertical line. So this is a swap gate which physically swaps the state of two qubits. Then we have measure. The symbols that look like speedometers or gauzes represent measurement. In quantum mechanics, a qubit can exist in a state of probability, which is superposition. However, you cannot see probability. When you measure it, the qubit is forced to collapse into a definite state of essentially 0 or 1. And the last one is result. The lines coming out of the measurement gauzes are double lines. So you can see the double lines here. This signifies that the data is no longer quantum. It is now classical binary data, which is in the form of zeros and ones, that can be read by a normal computer and shown to the user. Let us see few applications of quantum computing. And the first one is light switch. The image here uses a light switch to explain the binary system, which is the language of classical computers. In the physical world, a standard light switch is either on or off, but it cannot be both. Right? And here on position is represented with 1 and off is represented with 0. In the picture also you can see that. Just like you can't have a switch that is sort of on and sort of off at the same time, classical computer bit is deterministic. It is always in one definitive state. And also, you can see this. Classical computers, they always solve problems fast, one path at a time, which we have seen before. Because a bit must be either 0 or 1. So classical computers generally solve complex problems like finding a way through a maze by trying one path. And then they'll try the other. if that path fails, but they won't choose the multiple paths at the same time. So they do this incredibly fast, billions of times per second, but they are still checking options one by one rather than all at once. And here you can see two computer chips, 1 and 0. So one is glowing with label 1 and the other is dark with a red cross over this 0. This reinforces the idea that if a bit is 1, it cannot be 0. The two states are mutually exclusive. And the second application is dimmer switch. Unlike normal light switch, dimmer switch does not have just two positions. It can be completely off, completely on, dim, medium bright, half bright. It can be anywhere in between. So the light's brightness is not fixed. What this represents in quantum computing? See, a qubit is like a dimmer switch only. It is not limited to only 0 or 1 because or before measurement it can exist in a blend of states. So we can say that the light is not fixed in one state. Then just as the dimmer can be set to many brightness levels, a qubit can exist in multiple states at the same time. So which is nothing but superposition. Here you can see a glowing dimmer knob which shows continuous control, not a simple on or off. And the gradual light emission represents many possible states. The atom symbol hints that this behavior comes from quantum physics. The dimmer switch is just an analogy, but not a perfect match. A qubit does not store brightness levels, it stores a quantum state that becomes 0 or 1 when measured. And the third one is magic coin, which is an application of superposition concept. See, usually a normal coin can be heads or tails, right? At any moment, it shows only one result. There is no confusion. It is either 0 or 1, but not both. Whereas a quantum coin behaves very differently. It can be heads and tails at the same time. So this mixed condition exists only until someone checks it. This special situation is called as superposition. And in the image, the coin is spinning, glowing with digital circuits. The label 0, it is nothing but heads, and 1 represent tails. You can see both of them are connected to the coin. This means a coin is not fixed to one outcome. It represents a qubit but not just a normal bit. Then when you measure or observe this quantum coin, the superposition collapses. Okay, when we perform this measurement, then it collapses this superposition and the coin becomes either heads or tails. It can be either 0 or 1. There will be only single state. After measurement, it behaves just like a normal coin. And one more example for superposition is maze analogy. The maze represents a problem with many possible solutions. Each path in the maze is one possible way to reach the answer, and the exit of the maze is the correct solution. So, if it is a classical computer, see here, you can see one person standing at the maze entrance, and the red line it shows one path being tried. Say if the path is wrong, the computer must go back, try another path, which means there is only one solution at a time. It is very slow for large or complex problems, right? So, this is a concept of classical computer where only one solution will be tried at a time. Whereas, if it is a quantum computer, you can see many transparent figures spread across the maze, and each figure represents a possible state of qubit. All paths are explored at the same time. This is nothing but superposition in action. So it indicates that quantum computers try all solutions at the same time. So if it is a classical computer, it just try only one solution at a time. Quantum computers try all solutions at a time. Then why superposition helps? Because qubits can exist in many states simultaneously. So the quantum computer can explore many paths at a time. It does not commit to a single path immediately. Say when the computation ends, measurement selects the best or correct path. And here you need to remember one important point. That is, quantum computers, they do not randomly guess. Okay, so they use superposition and then interference concept. That means good paths are always strengthened, whereas bad paths will be cancelled. This increases the chance of getting the correct answer when measured. And the fourth one is magical twins for entanglement. Entanglement happens when two qubits become linked. After this link is created, they cannot be described independently. They behave as one combined system, not two separate qubits. Here in the image, you can see qubit A and qubit B. And there is a glowing twisted connection links them. So here you can find a glowing twisted connection which links both the qubit A and qubit B. This connection represents entanglement and distance does not break this link. So qubits become entangled. And say suppose if there is a change in one qubit state, other qubit also changes instantly, right? So if one qubit is measured or changes state, the other qubit, okay, the other qubit state is fixed immediately. This happens instantly no matter how far apart they are. So here, if you change one, the other changes instantly. And entanglement does not send messages or signals. Okay, so you cannot use it to communicate faster than light. It just creates strong correlation, but it is not created for information transfer. And you can see that entanglement qubits, they act like one system but not two separate ones. Then why this quantum matters? Quantum computing is not just theory, it's useful for solving real problems that normal computers struggle with. So you can see this. So this is useful for solving big problems, thus changing the world. And these are few applications. So it is useful in medicine, security, finance sector, etc. So if you take the first one, medicine, medicines are made by understanding how molecules interact. Molecules behave according to quantum physics. So classical computers, they struggle to simulate them accurately. Then how this quantum helps in medicine? Because quantum computers can simulate molecules naturally. They can test millions of drug combinations faster, predict side effects earlier, speed up vaccine and cancer drug research. And this is one of the best analogy. So instead of testing medicines one by one in a lab, quantum computers test many possibilities at once. And the second application is security. Today's internet security relies on encryption. Classical computers would take thousands of years to break it. Then, what is the quantum impact? So, it is actually having two sides. So, there is a risk with the quantum in this case because powerful quantum computers could break current encryption. But at the same time, it provides best solution also. So, quantum technology can also create quantum encryption, unhackable communication. And the best example is quantum key distribution. If someone tries to spy, the system detects it instantly. So we can just compare it with a magic envelope which destroys or changes the message if anyone tries to spy. Or we can even compare it with a super lock that changes its shape the moment someone touches it. And the third one is finance. Financial markets have millions of variables, constant changes, huge data streams. Quantum computers can analyze many market scenarios simultaneously, optimize portfolios, predict risks better, and even detect fraud faster. So, best example is checking all investment futures at the same time and choosing the safest and most profitable one. And you can even find a glowing chip in this picture. It represents a quantum processor, which is a brain of a quantum computer. And you can even find few flowing lines which show connectivity, massive parallel processing, information flowing in all directions. This represents quantum computers handle complex networks better than classical machines.